Okay, now this is the part two of the question. In the part one, we are looking in the part two, everything is the same like part one, but here we are trying to calculate the total pressure requirements at the operating conditions. So I will explain to you in this what do you mean by this total pressure requirements at the operating condition. But now here we have three more added parameters for this question, which is the viscosity at 4 degrees centigrade, which is the 43.5 centistotes, uh, pipe roughness. Okay, this is the property of the material, and this is the delivery pressure. Okay, now this is the diagram that we made in a part one. So if you don't understand this, please go back to the part one to see how this all what I was trying to explain here. Okay, now what here I want to explain again is that the at the outlet the customer wants us the pressure of 350 kilopascal. Okay, that's the customer wants us this pressure. Usually, whatever plant, wherever you are sending, the customer always have its own pressure and temperature and composition requirements at the outlet. So here we have the pressure requirements at the outlet. Now, if this is the outlet requirements, we are not going to install any pump or any pumping or boosting station in between from here to here. This is the customer requirement 350 kilopascal. What should be the pressure here at this point at the inlet condition so that the final pressure becomes 350 kilopascal? Okay, we say that the pipeline is horizontal, it does not have any elevation to to send have a pressure of 350 kilopascal. What should be the inlet pressure so that the pressure at the end reaches 350 kilopascal? Now, first of all, you need to understand that if there is a flow of the fluid from the inlet to the outlet, there will be a pressure drop inside this one. Why will be there will be a pressure drop? Because the fluid is dense, the fluid has viscosity, viscosity is resistance to flow, and then there's the roughness of the pipe is rough, so it gives a lot of resistance for this fluid to flow inside this pipeline, which slows and resists and reduces the pressure of this the fluid which is going inside. So whatever pressure you keep at the inlet conditions, as it moves through this pipeline, the pressure will drop, and pressure will drop because of the viscosity, density, and the roughness of the pipe. These are the main factors. So if the pressure will drop, and now the question comes here, how much pressure will drop? Okay, so this is the first step we need to know, because if we know how much the pressure is dropped, we can calculate the total requirement here in the initial stage. So this is the main question, is how much the pressure will drop inside this pipeline over kilometers per kilometer. So we have 200 kilometers. Let's say on each 1 kilometer, how much is the pressure losses can occur inside this pipeline? If we know this question, we can estimate the initial pressure here, and the outlet pressure we can get this one to 350 kilopascal. So that's the question here. So let's see how we do this. First of all, we need to know the flow rate. At this flow rate, what is the pressure? So in the step number one, we said that 794 meter cube per day. This is the flow rate we calculated in the part two. You can go back and look into it how we did that. Now in this case, what we did in the step one, we added the design load factor. Okay, so what is the design load factor? I already explained here also that the pipeline usually uh, they are not usually operated 365, and there are due some operational restrictions or maintenance going on throughout the system. So what we do, we sometime we increase, sometime we decrease. So the average flow rate that we keep, uh, that's we call it a load factor. So this is the ratio of operating days to calendar days is called the load factor, and it can be defined as the average daily flow rate divided by the actual maximum flow rate. So basically we divided multiply 1.125 as a design load factor with this one to get this value. So okay, once we have this one, the design factor, the step number two, we will convert this flow rate into the velocity. Okay, velocity becomes 1.21 meter per second. Okay, and the formula that we use in order to calculate this velocity is this one. Velocity is equal to 4 multiplied by the flow rate. This is the pi, which is 3.142, and the pipe diameter. So once you have this, we can get the velocity of the fluid, which is the 1.121 meter per second. Why we are doing it? Because we want to calculate how much we want to find out how much the pressure is dropping per kilometers okay, so that the final outcome pressure is 350 kilopascal. That's the main objective. So in order to do this, we have a formula here, which is this one. This is the pressure over time multiply is equal to the friction factor, density, velocity over by the density. So we need to calculate all those factors which are given in this equation. So in this case, we need to find the velocity, we need to find the density, we need to find the friction factor, and we need to find the initial the inside diameter of this one. So these are the factors that we are trying to calculate here. So in the step one, what we did, we converted the flow rate to the velocity, which is this one, which is required by the formula. And then, as I said, the number, we have to also find the friction factor. Now how we find the friction factor? Friction factor has a formula, which is by the friction factor can be found by the Moody's diagram. Okay, and this diagram, using this diagram, so this diagram basically need two factors. One of them is Reynolds number and another was the relative pipe roughness. These two factors, if we have them using this chart, we can find the friction factor. Okay, so how I did it here, first of all, we calculated the Reynolds number, which needs velocity as well as the viscosity of it. So this is the velocity, the number one. Then we have the inside diameter. So the outside diameter is given, the wall thickness is given, and based on the outside diameter and the wall thickness and correction, the conversion factor, we find out the pipe side inside diameter, which is 0.494 meters. Okay, and then after that we find the Reynolds number. Now in the Reynolds number, we this is the velocity, which is 1.21, we calculated through this formula. Then we have the inside diameter that we have it here, and then we have the viscosity, which is 43.5 centi-stokes. We convert them into the stokes. Okay, so we divided into 10 power 6. So this is the Reynolds number we found, 13,730, using these three one. And relative roughness also has formula. Okay, so here we use the pipe roughness, which is 0.057, and we divide it by the inside diameter 0.494, multiply by 1000, and we get the one, this relative roughness. So now we have the Reynolds number, we have the relative roughness. Based on these two, we can go back to the chart, and from the chart we can find the friction factor. So here's the this chart. So what we did, our first value here is 13,730. So here what we did, here you can see the 10,000 starts from this point. So the 13,000 somewhere between here at this point. Okay, and somewhere between here, and the relative roughness that we have here, if you convert this to this one, it is 0.00009. Okay, so this is 0.009, somewhere between, close to, less than this 0.001 line. Okay, it's somewhere between here. So this is the 13,000. We go ahead here, and if I put the line here in this one, so I put it somewhere between here, somewhere between here, and then I put another one. Okay, I will increase the weight. Okay, so here we get the 0.028 from here, friction factor. Okay, then after we have the friction factor, now we have the friction factor, which is 0.028. We have the pipeline inside diameter, we have the velocity. We can easily go to this formula. Okay, we put all the values here and we can find the pressure gradient. So friction factor, we find 0.028. We had already the density at 73.1. uh, this is the 1.121. Okay, but this has to be square, so you need to square this one here. So once you square this one and divide it by 2d, this is 2 and this is the inside diameter of it. Once you do this calculation, you'll get the the pressure gradient, which is 37 pascal per meter. Okay, so we now we want to convert this pascal per meter to kilometer, kilopascal per kilometer. So this is the pressure drop. So what does this value mean, 37 kilopascal per kilometer? What does this value mean? This means that for each kilometer we have a loss of 37 kilopascal. Okay, so now, for example, if 200 kilometers is, so each kilometer we will lose 37 kilopascals. Okay, so what we did here, we multiplied this by 200, and then we added the delivery pressure, whatever we have, 350. So this is the requirement of 7,750 kilopascals gauge here. So it means that if you keep the pressure here 7,000, yeah, 7,750 kilopascals. Okay, if you keep the pressure here 7,750 kilopascals, and you run this pipeline for 200 kilometers, the outlet pressure will be 350 kilopascals, because there will be a pressure drop here of about 37 kilopascal per kilometer. So there will be a pressure drop. So each kilometer, this pressure is dropping, and over time, once it reaches the outlet condition, it will end up with 350 kilopascals. So that's the question number two in this one. Okay, so just a review of this question, what we did here in this case, first we find the design factor. We added the design load factor and multiply this number with 1.125. And after that, we converted this flow rate into the velocity, because the formula requires it, okay, in meter per second. Then we determine the friction factor. Friction factor we found through Moody's diagram, where we have the Reynolds number and the relative roughness. So we need to find out these two values. Reynolds number can be find out using this formula, where we have the uh, velocity, diameter, and viscosity. So here is the velocity, we had the inside diameter, and then we had this viscosity, and we find out this is Reynolds number. Relative roughness is based on the pipe roughness, which is 0.047 divided by 0.494 and multiply 1000. And using this formula, we found out using this friction factor. Then after we have this friction factor, we have the velocity, we have the viscosity, and we have the inside diameter. We plug in all the values here. And then we find the 37 kilopascal per meter, which we convert to 37 kilopascal per kilometer. And then if you multiply this by the length of the pipeline, which is 200 kilometers, and added the customer's requirement 350, so we find out the initial pressure. So it means that if you keep the initial pressure 7,700 kilopascal, and the customer wants 350 kilopascal, you need there will be a pressure drop of 37 kilopascal. Okay, in this case, we assume that a pipeline is straight, okay, is horizontal and does not have any elevation. What if the pipeline has elevation like this? It is going up, it is going down, it is, you see, it's going up, it's going down. And that's what our next question, my next video will be on this one.